Hi everyone and welcome to the new video. With this video I want to start a new series about data science and data processing, and I will start with an interesting topic that I personally never saw on YouTube, with processing astronomical images. It is an interesting area because astronomical cameras see the world differently compared to other cameras, so it is interesting to see how it works. In general, astrophotography is the most complicated part of the photography. Most of deep sky objects are very dim, and photos are obviously taken at night. These images require long exposures, and even this is not enough. We need to stack these images together to improve image-to-noise ratio. I will show how it works. So this is a very challenging and interesting area for Python processing, for using scientific frameworks like OpenCV, NumPy. Also, this topic is not purely theoretical. Not so long time ago I bought an interesting device, a smart telescope. It is a small portable device that can be easily placed on your balcony and you can make your own images. So in Python I will process real images that were taken from my balcony. I live in the city, it is not a village, and as everyone knows, stars are not very good visible in the city. So if I was able to do it from the balcony, then you can do it as well. And by the way, this video is an experiment. I really don't know if there are many people interested in data processing. There are various interesting topics like analyzing the radio signals or gathering statistical information about published songs or something like this. But obviously if nobody is interested, there is no reason to make these videos. Maybe more people are interested only in short tutorials. So write your thoughts in the comments, I would be curious to read it. But anyway, I believe that astronomy is an interesting science, and also while doing this you can learn a lot about OpenCV, about image processing. So it can be fun. Let's get started. As a first step I will explain how the smart telescope works. As we can see, it is a pretty compact device, it's not very big, and it's also not very expensive. Its price is like a smartphone. So technically it's like a smartphone camera combined with the lens and the motor inside. It is named a telescope, but technically we cannot watch through it. It has a lens, but there is no eyepiece, there is no screen. All controls are made by the smartphone. I can show how it works. First I need to turn it on. As we can see, it needs some time to boot, probably there is a Linux inside. And after that I can connect my smartphone to the telescope. The telescope can work as a Wi-Fi access point, which is useful in the field, or I can connect it to my home network. Then I can activate the telescope. I need to wait a bit. Of course, now I'm doing this at the daytime, so nothing is visible. But if I do it at night, I can select an object I would like to see, for example a deep sky object or planets. And then a smart telescope will automatically stack the images and show the result. The general idea is that the deep sky objects are very dim, so the telescope is taking a lot of photos. Each photo is about 10 seconds and the total process can take about an hour. And when we make lots of images, the camera's noise is random, but the signal is real. So when we stack these images, the signal to noise ratio is increasing and we can see more and more details. Normally the telescope is doing it automatically, but there is an option to enable saving all the frames to memory. The process can take a long time, for example 1 hour, and when we are ready we can download all the frames. We can just connect the telescope through USB and I can download the files and I can process them. So this is how I collected the images. And now I can process these files in Python. Let's see how it works. Okay, let's get started. For this project I will be using a Visual Studio Code. First I will create a Jupyter Notebook. It's a convenient way for data processing and I will show how it works. Here we can run code in the interactive Python cells. Let's also save the file. And now we have an open project. Before we begin, we can remove this AI spam, we don't need it. And let's get started. As the first step, I will read the data I got from the telescope, and I will get a list of files I have. This telescope is saving data in the so-called feeds format. In Python we can do it easily in this glob method, and here I can just specify the mask. This is the folder I have. And here we can see the files I have. I can also print the number of total files. Let's see what we can get. And as a result we can see that I have 391 files. And now let's read them. Luckily for us, we don't need to implement this from scratch. There is a library called AstroPy. But as we can see, it's not installed yet, so I need to run this command. If I run it now, I will get an error. But in Visual Studio Code, there is a convenient way that I can show you. And this package will be installed in this environment, so it's convenient. I don't need to switch to console. And as we can see, it is running. And I can rerun the cell again. Jupyter Notebook is convenient for data science because, for example, if I run this cell, this data is stored in memory and I can use this data in next cells. I don't need to rerun it again. And this is very convenient if we have a lot of data and processing can take, for example, 30 seconds. And I can work with this data. For example, I can print files from zero and we have this data and I don't need to run it anymore. And now let's see how this AstroPy library works. As a next step, I will create a method load fits data. Obviously, the type of data is NumPy arrays, we can see. The shape of data we can see on the screen. This is the resolution of my telescope. And interestingly, we can see that this data is monochromous. The telescope has a color matrix, but we need to process it, and I will show how it works. This is a raw data, we need to process it. On the screen I can see raw data, but it's not a classical RGB data because, for example, this value is 358. This is bigger than 255, so this is bigger than 1 byte. Let's first print the maximum and minimum so we can see what is the data here. So I suppose that this matrix or this telescope can return us 16-bit data. To verify it in more detail, I can build the data distribution with Matplotlib. It's also an important library that I will show. Matplotlib has a useful feature for that, to draw a histogram. And it is a pretty convenient way. I can create a figure and I can set the colors. It's just to make it more beautiful. It is a big white. I can make it smaller. And here we can see that most of pixels are in the range from 0 to 400 or to 500. I think that this data is 16-bit, it's 2 bytes, so it's from 0 to 65535. But because of the sky is dark, we have the distribution in the low part of this spectrum. Okay, now we are able to see the distribution, and now let's try to visualize the data. To do this, I will use a log normalization. And I'm also rotating the image just because it fits better to the screen. And wow, we can see our first stars. The data is not processed yet, but we can see the image. This is great. Let's go forward. Okay, at this moment we were able to load the feeds file and we were able to see our first stars. But of course the real processing is more complicated, so let's see how it works. And to do this, we first need to understand how the astronomical cameras works, because astronomical cameras works really different compared to normal cameras. And in general, we have several types of astronomical cameras. Some cameras are monochromatic. Because of that, they can make a high resolution image. And by the way, some photography cameras as Leica also have monochromous images, and some photographers like this. So this is the first approach. A second approach is to use the filter wheel, so astronomers can make several photos with, for example, RG and B filter, and then they can combine the data together. The advantage of this method is a higher resolution, but it takes more time to get photos because technically we need to get photos 3 times. And the third way is a so-called Bayer pattern. The camera matrix has an array of micro lenses, and the algorithm combines the image together, so these lenses are RG and B, and so we have actually 3 types of pixels on one array. And then the special algorithm converts this image to a normal RGB image. This telescope is using this approach, so we need to run the algorithm and we will get the RGB image. Let's do it. The mathematics can be complicated, but luckily for us, OpenCV has a method for it. Here I created the method process image. Also, as we can see, I am using this constant. As you remember 5 minutes ago, I had this distribution, but most of algorithms, they work with normal RGB data like 255. So I need to make this smaller, and the easiest way is just to divide it by 2. So technically this approach is simple. I am using OpenCV. I am using this parameter color bias to RGB. And as we can see, I create an RGB data from our raw data, and let's see how it looks. And as we can see, now it is much better and we can see a real sky. But we're only approaching the fun part. Let's go forward. Okay, at this moment we were able to get an RGB image, but interestingly, astronomical cameras process images not like normal cameras do, because normally we just take a photo and that is it. But in the astronomical images, deep sky objects are dark, and we just cannot take this photo in one image, it will be nothing visible. And the real idea behind the deep sky astrophotography is taking the images. And the idea is that object is real. For example, we see something in the center, but we cannot recognize it. But the sensor noise is random, so when we stack images together, we increase the signal to noise ratio and we can see much finer details. So let's do it. Of course, the process is challenging and that's why it is fun to do it. Let's get started. As a reminder, I have about 300 images. Every image has a 10 seconds exposure, so I can stack them together. But to verify that I can do it, I will first load 2 random images and I will see how they look. To do this, I will load 2 frames and I will compare them one by one. I just selected a random photos, I selected the first image and I selected an image with the index 100. Here I can create 2 images and let's see how it looks. And here I can see that I cannot stack images together as is because, for example, this pair of stars is in this corner, and here this pair of stars is much further, it's at the right, so I just cannot combine one image to another. Originally I didn't expect this, but this telescope is a budget one. Normally telescopes have a so-called equatorial mount and they track the night sky. The Earth is rotating, so we can see that the sky is moving, and the equatorial mount allows the telescope to track this movement. But first, it is a budget telescope, it has an alt-azimuthal mount, and second, apparently this tracking is not very accurate. As a next approach, I will print this image as a GIF, so I will see this in the animation form. It is much easier to understand. I will be using this library to create a GIF, and I will save the first 50 frames in a file. Let's see how it looks. I updated the components by running this command, and now let's run it again. As we can see here, I am also using TQDM library, which is convenient to show the progress bar, and saving the frames takes some time. And now it is done. Let's see what we get. And I can open this image and I can see that it is really jumpy. So we have a challenge to synchronize it. Let's do it. Okay, at this moment we were able to get the RGB image, and we verified that we cannot just stack them together as is because all stars are in the different positions and the telescope is doing the tracking not very accurately. So I will use an object tracking to fix this, and to make it easier for the algorithm, I will preprocess the image first. So our processing pipeline will consist of several steps. First I will convert the image to the grayscale and I will increase the contrast. Then I will use an object tracking algorithm to track the specific frame, for example this one. But this algorithm is not very accurate, so I will use additional code to pinpoint the star, and I will use it as an anchor point. So let's see how it works. As a first step, I will add some helper methods. For example, I will apply the gamma to make the image brighter. And this is our preprocessing. I'm applying gamma to make the image brighter, and I'm also converting the image to grayscale, but the object tracking algorithm requires RGB, so then I convert it back to RGB. As a next step, I will create a method to get the maximum brightest point. We have this method in OpenCV, it just gets the point from the specific area, we will use it later. And as a last helper method, I will create a method to draw on frame. It will be useful for debugging because we will see how the algorithm works. And now, as an example of this approach, I create 2 rectangular areas and I'm getting the maximum point and I'm drawing it on frame. Let's see how it works. So here I was able to increase the contrast. I created 2 rectangles of interest. This is the first one and this is the second one. And as we can see, I was able to get the maximum brightest point. So this is our preprocessing pipeline, and now I will run the object tracking. First I will test it with 3 images, so it's faster and I don't need to wait too long. I'm also creating our region of interest. These are two boxes. For this area of interest, I selected an area which has a bright star on it, for example, this one and this one. This area should have some specific shape. For example, I have like this triangle. The first frame in the sequence I will be using as the initial frame, so all other frames I will be moving to the first one. And this is our main loop. The object tracking is implemented in OpenCV, so I don't need to use any extra libraries. As we can see here, I'm initializing the tracking using the first frame, and for the current frame I'm preprocessing it, and I'm updating position 2 times for 2 regions. So this code is long, but technically it is easy. First I created an object of interest, then I will store my data as an array, because later I will use it to move the images. Then I initialize the object tracking with the first frame, and then I'm finding the same object on the second frame, and I'm doing it 2 times because I have 2 regions, and actually that is all the code. Let's run it. And as we can see, it works. We were able to detect the same frame, and we were able to detect this on 3 different images. So we can see that object tracking is working, and we were able to detect the same star, and now we can rotate and move the image. Okay, at this point we have a list of original frames, it is here, and we have a list of anchor points, so we can move all the frames to the first one, so we can stack them. Let's do it. First I will keep the original frame as a reference, so we can move other frames to the first one. When I checked images manually, it turned out that I not only need to move the frame, but I also need to rotate the frame. Because here, for example, we can visually see that this angle is a bit different than that angle. And it happens because of the Earth's rotation. More professional telescopes, they have equatorial mount. It automatically tracks the sky, but this telescope does not do this. Now I will create an array for the final result, and I will process all the frames except for the first one. As I mentioned before, TQDM is a useful library to show the progress bar, but it is optional. And first let's calculate the angle. And now I can rotate the image using OpenCV. I'm creating the rotation matrix with this difference, so all these frames will be aligned. And when the image is rotated, I need to shift this. And finally, I need to save the result, so all the results will be in this array. I will use the same code to show the frames, so we can see the result, and let's run it. And as we can see, it works. Here we can see a funny difference in rotation, but as we can see, these stars are aligned perfectly, and these stars are aligned, so visually it looks good. It also turned out that some frames have bad quality, for example, they are blurry, or maybe it was a gust of wind and the telescope shaked a bit. And optionally I will save the frames to PNG files, so I will check them manually. And now we're ready to the final step, to stack the images and see the result. Okay, I manually checked the images out of camera and removed the bad ones. So first let's load it. I will also use a helper function to load the image. I also exported images to GIF, so I will show how it looks, and as we can see, they're aligned properly. And the stacking is technically simple. First I'm creating 3 channels for RG and B, and then I just iterate through my images and I combine the data together, so it's pretty simple arithmetic operation. Then I can merge all 3 channels to one image. I know that in OpenCV we use BGR sequence, so I am using this one. And the moment of truth, let's see how it looks. Okay, now we can load the image and we can see that all images are loaded. And as we can see, the result is much better, and we are almost ready. First I will adjust the white balance, because this white balance looks not correct. And as we can see, it is much better. As we saw, the image was a bit reddish, so I adjusted the white balance. Of course, in the normal cameras, white balance is adjusted automatically, but here I did it manually. And we can do it even better. Let's adjust the brightness and contrast. I'm using this OpenCV method, and let's run again. And here we can see our object in the proper shape. As we can see, there is a galaxy here. And the last but not least, we have this white border, so let's add some crop. I added a margin of 120 pixels, let's run it again. Okay, this is our final result, and let's summarize what do we get here. As an original data, I had about 350 raw images from my telescope. These images had different rotation and different position. So first I applied the object tracking, and then I rotated the images so all images are in the same position. I also moved the images so all stars are aligned. Then I stacked the RGB layers together, and the magic behind is simple. The noise is random, but the object is real. So even if nothing is visible, when we combine the images, we get much better signal to noise ratio. And as we can see, the noise is almost gone and the image is much brighter. I also applied brightness and contrast, and we can see the final result. And what do we get here? It is a reflection nebula IC5146. This is an interesting object of magnitude of about 9, so it's not visible by the human eye. And this cluster is located about 4000 light years away. And as a comparison, this is the image from Wikipedia. Of course, it is much better, but we shouldn't forget that this telescope is small and it is located on my balcony. In the dark sky, your result will be much better. And that's it for this video. Thanks for watching. I hope you learned something new. Astronomy is a fun science, and OpenCV and image processing is also fun, as we can see. If you want to see specific deep sky objects from this telescope, let me know in the comments below, and maybe I will make a second video. Also, this video is an experiment. I have no idea if there is a public interest for that, so please write in the comments below if you want more videos about image processing or OpenCV. But it was fun to do it anyway. The source code for this project is available on my Patreon page. I will also put the image samples there. I'm going to make more videos about data science and data processing, so stay tuned and subscribe. And thanks for watching, and see you next time.